welcome in chemistry education lecture series. Today, in this video, we are going to see the volumetric analysis. Under this volumetric analysis, there are a number of titrametric methods are there, out of which here we will see the redox titration method. Now, redox titration method is, we can define, it is a chemical reaction in which the electrons are transferred between the two reactants participating in it. This transfer of electron are identified by observing the changes in the oxidation state of the reacting species. That is, in this type of reaction, we observe that two reactions, first is the oxidation reaction and another is the reduction reaction. And these two reactions simultaneously reacted with each other. This is called as the redox reactions. Now, for example, metal ion solution, when treated with the another metal, we get the formation of first metal plus the another metal ion solution. This is the redox reaction because here it is a combination of oxidation and reduction reaction. Now, for example, in case of the copper 2 plus ion, this is the solution, and when zinc metal is treated with the copper ion solution, then the zinc gives the two electrons and it gives the formation of zinc 2 plus ion. This is the oxidation reaction, and when copper 2 plus ion accept these two electrons to give the formation of copper metal, this is a reduction reaction. Now, in this way, the copper accept two electrons to give the copper. This is a reduction reaction. It is also known as an oxidizing agent. And when zinc gives the formation of loss of two electron and to give the formation of zinc ion, this is the oxidation reaction, and it is also called as a reducing agent, or it acts as a reducing agent. Now, what happened when we are observing that in the solution, initially it was a copper solution, and when we are adding the zinc metal in the solution, then zinc get converted into the zinc ion, that is a colorless solution, and copper get deposited at the bottom. Now, in this way, the copper 2 plus ions get deposited in the copper metal, and zinc metal get dissolved or to give the formation of zinc ions. Now, zinc gives the two electrons, and that is the oxidation takes place, and it acts as a reducing agent. The reduction potential is equal to 0.76 volt. Now, in this case, this is the copper solution, and when we kept the zinc rod in the copper solution, then what happened after a certain time, it is observed that, see here, whatever the copper present here in the ionic form, it get deposited on the electrode, and from the zinc, the zinc get dissolved into the solution, and the color of the solution becomes colorless because it gives the formation of zinc solution. Now, this is the, in case of the copper, this is the reduction takes place, and in zinc, it is oxidation takes place. Now, redox reactions or titration is a volumetric method of the determining of the concentration of the given analyte by causing the redox reaction between the titrant and the analyte. These type of titration require the use of potentiometer or redox titration indicators. Now, with the help of indicator, we can measure the concentration required to complete the oxidation and reduction reaction, or with the help of potentiometer, we can measure the EMF of the solution. We get the titration curve, and from that extrapolating, we can calculate the exact equivalence point of the titration. Now, for example, this is a titration, potentiometric titration method. Now, in this method, we know that the galvanic cell, this is a chemical reaction which gives spontaneously to produce the electrical energy. From the chemical reaction, the electricity is generated because the oxidation reduction reaction takes place. And sometime what happened, the electrolytic cell, where electric energy we have to supply to the solution by force to give this spontaneous chemical reaction. Now, for example, in case of this the Fe2 plus ion solution, we have to take into the beaker, and then we are adding the steric solution from the burette, and then we are measuring the EMF change. Now, by keeping the two electrodes, reference electrode and one is the platinum electrode, then where the ferric ion solution with the green color solution, when we are adding the ferric ion solution from the in the ferrous solution, we are adding the ferric ion solution, it get converted into the ferric ion, that is ferrous to ferric and ferric to ferrous. Now in this way we can see here the green color solution is get converted into the colorless, where we are adding the ferric ion solution to give the ferrous solution, and whatever the ferrous ion solution is that there, it will convert it into the ferric ion. Here the ferric ion solution get converted into ferric and ferric ion get converted to ferrous. In this way the oxidation reaction and reduction reaction took place simultaneously, therefore it is called as a redox reaction. Now the example we are taking, the example of the KMnO4, it is a strong oxidizing agent. Now KMnO4 dissociate into the K plus and MnO4 minus. Now in this way it dissociate in the when we are taking the acidic solution, then the reaction is 2 MnO4 minus plus 8 hydrogen ion plus 5 electron to give the Mn2 plus. Now here Mn7 plus get converted into Mn2 plus. The standard reduction potential is 1.51 for the KMnO4. Now in alkaline medium what happened, the MnO4 minus get converted first into the 2 minus, and then for this purpose we require the 0.56 volt as a reduction potential, and from MnO4 2 minus plus 2 H2O plus 2 electron gives MnO2. For this reaction we require the 0.60 volt as a standard reduction potential. Now another indicator, that is a K2Cr2O7, this is also oxidizing agent and it can be used as an indicator for this titration. It is a less powerful than the KMnO4, okay, but K2CrO7 is used only in acidic medium, but KMnO4 can be used in the acidic as well as alkaline medium, and it reduces to the room temperature. Now here the Cr2O7, which has a orange color, and when it treated, then it converted into the Cr3 plus, that is a green color. Now where the standard reduction potential is 1.51 volt. Now in this way the K2Cr27 or KMnO4 can be used as an oxidizing agent. Now some indicators are there. Now these are the weak reducing agent or oxidizing agents are there. Now indicator plus 2 number of electrons and gives the indicator red color. Now this reaction can be transferred here. Now for example 110 phenolphthalein. Now in this case what happened, the Fe2 plus salt react with indicator to give the formation of complex that is called as a ferrion indicator. Now this ferrion indicator get converted into the blue color. Now initially it is a red color and then it converted into the blue color when after loss of 1 electron. Now in this way this indicator form the complex with the Fe2 plus, and then we can use as a redox indicator for this titration, and the color change from the red to blue color. Now another indicator, that is a diphenylamine. Now this diphenylamine, after oxidation what happened, the two molecules of this diphenylamine react with each other to give the formation of colorless diphenylbenzidine. Now this gives the colorless solution, and after next oxidation of this, then immediately it gives the purple color. Now in this way the this indicator shows the colorless to purple color, or when we are using this indicator as a green color, then this green color is converted into the purple color through the colorless. Now in this way diphenylamine is also oxidizing and reducing agent, can be used as a color from the green to purple or purple to green. Now another third indicator is a potassium permanganate. It is a self indicator. It can be oxidizing agent as well as it can be used as a self indicator. Here the Mn7 plus, that is in purple color, they get converted into Mn2 plus. In this way the purple color get colorless. We can use as a potassium permanganate in the same reaction as well as a self indicator, because it has its change in color from colorless to pink color or pink to colorless. In this way these type of indicators are used. Now when we are using this titration for the determination of strength of H2O2, now for determination of H2O2, we require the oxalic acid KMnO4 as an indicator. Now for we can prepare the standard oxalic acid solution by knowing the known for procedure. Then KMnO4 we have to prepare the nearly equal to the 0.01 normal KMnO4 solution. For this purpose we require the 0.790 gram and dissolve to the total solution is 500 ml. Now for standardization of KMnO4 solution with the help of oxalic acid, the 10 ml of oxalic acid plus we have to add the 10 ml of sulfuric acid, then we have to heat it or warm up to the 70 degrees Celsius, and then we have to add the KMnO4 by drop from the burette, and this gives the value related to where the colorless to pink color remains there. When you are adding the KMnO4 from the burette, it gives the pink color, and after shaking it disappear, and when it gives the permanent pink color, then we have to measure the volume required for KMnO4 for reaction with the oxalic acid, and from this we can calculate the exact normality of the KMnO4, and once you know the exact normality of KMnO4, it can be used for the titration with the strength to determine the strength of the H2O2. For this purpose, 10 ml of H2O2 solution is taken. Then we have to add the 10 ml of sulfuric acid, and then we have to titrate with the KMnO4. From the normality of the KMnO4, we can calculate the normality of the H2O2. And when you calculate the strength, then normality into equivalent weight is equal to whatever the strength is there. From this formula, we can calculate the strength of H2O2. And this is in related to the gram, but when we are thinking about the volume in terms of the volume, then we have to multiply this by the 22.4, and this is the B liter of the related to the H2O2, and from this relation 2H2O2 gives the 2H2O plus O2. Now 68 equivalent weight and then 32 or 22.4 liter at an NTP, and therefore this 22.4 we have to multiply with this gram, then we can calculate the strength of H2O2 in terms of the liquid volume. Now in this way we observe that in the volumetric analysis the redox titration and oxidation reduction titrations. Thank you.